Okay, for the first problem, well, we have to solve the Beer-Savart law. To solve the Beer-Savart law, first we have to get the cross product between the differential of line that is in the z-axis and the separation vector. The separation is kind of like, well, it's like the hypotenuse of the triangle that goes from the current to the test point. And well, when we get this cross product, then we have to use the trigonometric substitution. That it's basically using the cotangent of the triangle, and then we have to clear the set and then perform the derivative of set, so we can then replace those values in the Beer-Savart law formula. And well, first when we do this, we can get the rho value out. The rho is basically like the perpendicular distance from the current, well, yes, from the current. Well, when we get a rho out, we can then use tables and simplify this and cancel out the cosecant with the new cosecant and the rho value that we got with the rho value that we had in the numerator. And we can then get, using tables, we get that this gives us the sine of alpha, and when we perform the integral for sine of alpha, we get minus cosine of alpha, and well, we get minus cosine of alpha. Yes, and that minus cancels out the other minus that we got at first using the, the constant that we got out from here from the derivative of set. Well, and then we finally get that the final formula. Well, to get the final formula for the magnetic field, we just have to add the permeability in the numerator, and we get that it's cosine of alpha 2 minus cosine of alpha 1. And the cosine of alpha 2 minus cosine of alpha 1 will always be a positive number because, well, cosine of alpha 1 is basically like outside of the triangle. The one that is inside of the triangle is cosine of alpha 1 prime. And cosine of alpha 1 will always be a negative value, and that's why this operation will always be positive. And then, well, to get, we did this in class, but to get, basically to get, this is a very resumed version of it, but to get like the cosine of alpha 2 and cosine of alpha 1, we basically have to use the law of cosines. And well, basically, like in the triangle, we have the A, B, and C. And what we did in class was basically multiply, well, just like the vector of C times the vector of C would be equal to vector of A minus B times vector of A minus B. When we expanded that, we got like, the expansion like A squared plus 2AB plus B squared. And when we rearrange that, we finally got like that C squared was equal to A squared plus B squared minus 2AB cosine of alpha AB. And when we cleared cosine of alpha AB, we got this division. And then replacing just like replacing the angles, right? Like and then, well, using like the adjacent and the opposite and all that, we got the cosine of alpha 1 prime, that was the one on the inside. The cosine of alpha 1 was the one on the outside. And we got that cosine of alpha 2 and cosine of alpha 3. Cosine of alpha 3 we don't need. We don't need that. But cosine of alpha 2 was basically this, and cosine of alpha 1. But to get cosine of alpha 1, we just have to perform this operation, well, to basically use cosine of pi minus alpha 1 prime. That would give us just, well, basically cosine of alpha 1 was basically minus cosine of alpha 1 prime, and that's why it only changes the sign here. And then when we got this, we finally, well, we could use this sum, that is, a positive number, to get the segments. Now, to get the segments, what I did was basically like, since every value of the square is the same, like this is A and this is A and this is A and this is A, basically the segment 1 and segment 4, which it was very stupid, well, no, but basically like segment 1 and segment 4 are basically the same magnitude, they just change in the direction. And well, basically, to get the segment 1, if we get the segment 1, we got segment 2, the segment 4. And for example, if we get segment 3, that I will show you right now, if we get segment 3, we also get segment 2. And because they are also the same magnitude, they are basically the same face of this rectangular shape. Well, not rectangular, it's triangular, but has a base, square shape, square. Well, basically, to get this, we have to get the value of a, b, and c. That is basically, a is basically like a minus b squared. And well, we have to get xa minus xb, ya minus yb, and that's it. And well, we basically got that a is equal to a, and then for b is almost the same. Well, no, it changes. It depends on the points we choose for b, for a, and for c. Well, not choose, is the ones that we have to use. But basically for b, it would be like b minus p, the position vector, the position point, the position. Well, yes, and it would be like c minus p, and c minus p in x, in y, and in z, and you know the square, and then the square root. And then for c, it would be the same as in b, just replacing b and c, like it would be b minus p, and b minus p, and all that. And then when we got those values, we replace them in the final formula that we got here and here. Well, that's before the permeability, but yes, when we replace, we see all the terms that cancel out, and we finally get this. And this will be the same for this, as I said. But here we also to get the direction, we have to perform this cross product between the current direction vector and the test point direction vector. And it's basically like just to get the final direction. When we perform this cross product, we get that this the segment 1 is in the x direction, and it makes sense. And the segment 4, when we perform that same cross product but with the new points that we, for example, here it says that there's no values for x in the x vector in the segment 1. As we can see, there is no values, no. But for example, because it grabs the current vector is y positive, like you see as there is this here. But for segment 4, the current vector is this one here, that is minus x, and here is in the cross product minus 1 in x. And well, the row vector is the same for both, because, well, as we can see, here it goes from this point to z. It like increases in z, and that's it. And in here it also increases in z. So it's basically the same for both the row vector. So that's why it's both present in z vector and in z vector. And we perform the cross product for the segment 1. We get that it's in the x direction. We perform the cross product for segment 4. We get that it's in the y direction, and that's it. Now for segment 2 and segment 3, that it will also be the same as I discussed earlier. We get that, well, to get the segment 2, we do the same to get the a, b, and c, and then replace them in the formula, and then we cancel out all the equal terms and all that, and we get that it's this in the phi direction. But to get the row, as we can see here, to get this row, in the earlier problem it was easier because it was just like an A, because but here it's different because, well, we have to use the recipe for row, that it's basically the director vector times any vector. That letter, it's just a random letter we chose in class, but I use the same. And basically the director vector is just like the difference between the, when we look at the triangle, we will see that the director vector is basically like the difference between B and A to get like this side of the triangle, and the other vector is like going from the point from A to the point, and it's also a difference too. So when we perform that cross product, it will give us that it's it gives us the cross product here on top on the numerator, and the director vector, well, it's just present on the x-axis, so we just use A there. And then yes, when we perform this division, we finally get that the row will be equal to this square root, and then we replace it here in the final, well, in the formula. We perform all these cancellations, and then for segment 3, as I said, it will be the same, exactly the same, only that, well, if you want to do it and to prove it, you would see that B is and B and C change, like interchange, like exchange it with each other, because, well, when we choose these points here, with the B point would be the A point for segment 3, and the B point here would be the, no, here's not a point, but yes, that's basically it. Like, it changes the points, and that's why it would change the values for B and C. But when we perform the same cancellations that we did on top, we will get that it's the same, basically the same. And also with the row vector, that it's basically the same, that goes from here to there, and from here to there is the same value, it's the same magnitude, so we can leave it as the same, and we get that it's basically both are equal and in the phi direction. And yes, that's it for to get the total value for here. Well, yes, to get the total value for B, we just use the sum of segment 1, segment 2, segment 3, and segment 4, the total sum, and that's it. Okay, for situation 2, well, firstly we have to get the differential of line, the separation vector, and the separation value. To get the differential of line, we can see here, very small, that it's, well, basically when we look at it from the xz plane, we can see that there's the radius, the row value, times, it's just the radius times the differential of the angle, that small angle there, and this gives us the differential of line in the phi vector. And then for the separation vector, we just, well, it's basically the hypotenuse, as I was saying earlier, that it's basically the separation between the point given and the point chosen to, well, not chosen, the point we have to choose. And, well, when we perform this difference, we get the result, and we will continue to expand this and giving it the proper vectors. We see here that we have the row vector there, so we just replace it there in the formula. And then when we have the radius vector there, well, yes, the radius there, we just change here the vector in yes, the y vector to z, so we can be in cylindrical coordinates. And finally, to get the separation value, is just like a little Pythagoras theorem, the square root of the squares of the sum of, yes. And then when we perform this cross product, well, we get this result here, that it's a little crossed out and messy, but it's basically the first term here, the first component, it will be cancelled out because of the symmetry. When we look at this little graph here, we will see that since it's in the horizontal axis, the row vector, it will be cancelled out, since, well, each how to say, like, because of the circular symmetry, for every current that it's at any angle, there will be another element at the opposite side of the circle. And when we have this of equal magnitude and the same direction, that they will be cancelled out. And, well, yes, when we cancel this out, well, as we can see here, for example, when we perform the integration for this whole result of the cross product over the separation, we get these two components. But since we know that this will be 0, we can try to find why is it 0, right? And we can see that this over here, this term is not 0. This integration of here it's also not 0, it will be 2 pi. And this over here might be 0, the vector, the raw vector. So when we try to find out if the raw vector is actually 0, well, it's not, because, well, here we can see that this absolute value of rho is just like the just the square root of the x component and the y component in the raw vector. And since we know that the square root of cosine square plus sine square, well, no, not square, but sine square plus cosine square is equal to 1, and square root of 1 is 1, we can see that it's different from 0. So this makes us skeptical of the Beer-Savart law. But, well, yes. And then when we when we try to find out the second, for the second point, it will be basically the same. That, well, yes, because of, like, you know, the right-hand rule and the distribution of current, we'll see that it will also get cancelled out in the horizontal axis of this right here, since there is where this term here, this component here, is set. And, well, yes, when we see that, well, also this term over here, this second term, this second component, survives, well, because of, like, it's on the z-axis, so it's just like reinforced with each other. So yes, and, well, basically that would be it, I think. Wait, let me see. No, okay. And also, like, this basically shows like the dipole nature of the magnetic fields, that it cancels out at some, yes, because of the magnetic fields generated by current loops. And, well, yes, I think that's it. Okay, for the third situation, it asks us to find the magnetic field due to an infinite current sheet that is flowing in this direction, and it gives us this observation point at the top. And, well, because of the current sheet that is right there, it's kind of ugly, but yes, we have to use this formula for the density, that is current over length. And also, because of the symmetry, we have to assume that it has an infinite number of wires. Well, that's already said in the problem, and we will have to solve it in the using these points of y. Well, analyzing the y-axis. Well, basically, what we have to do first is find both separation vectors. Well, firstly, I find, well, the first separation vector that is going from the positive y to the observation point. It's basically the point minus the y, right? So we have to find this distance right there. So, well, basically, after performing that trace, we get this vector for the separation. And to find the raw vector, we have to basically do this the division between the vector and the separation value. And the separation value is just like we've already done in the past exercises, that it's like the Pythagoras theorem. Well, yes, after performing this division, we get this raw vector, but to simplify it, we can write it just as this, as a comma minus b, because here is negative, this is the value for y, well, for the y vector, and 0 because in z there's nothing. And, well, then we perform the cross product between the length vector and the raw vector, which will give us a phi vector, right? So, well, after performing the cross product, we will get this as the final phi vector for the the one in the left. Yes. And now, from the negative y to the observation point, well, it's basically the same, just changing the signs. Well, we have the like, for example, instead of, well, because the vector will be also the same, the point minus the y point, but because it is negative, it's minus minus, so it turns positive. And then after performing that sum, it will just change us the value for y, well, the sign for y. And the separation is the same because, well, it's the same magnitude, same direction. Yes. Also the new phi vector, well, after performing the cross product between the raw vector and the length vector, it's basically the same, just changing the sign for I think yes, for b, because, well, for b in the y vector. And, well, after performing that cross product, we get this final phi vector, right? Okay, so now that we have both phi vectors, we will find the value for the h vector, which is basically just the sum between the h in the first vector and the second vector, well, the sum, which will give us this negative h in the y vector, right? And now we have to perform the, I think is the correct, yes. Well, we have to perform this sum of integrals to, well, for the, because now the final objective is to find the magnetic field, right? So, well, first we have to find, yes, we have to use the, it's yes, the trajectory. The trajectory for the ampere, well, the Ampere's trajectory, which, well, basically goes from the segment, well, 1 to 2 to 3 to 4 and to finally to 1 again, like a loop, right? Well, for this top, well, the horizontal axis is the y-axis and the vertical axis is the x-axis. These values on top are on the x0 axis, and the values on the bottom are on the negative x-axis, well, negative x, and negative, here is on the negative y, here is on the positive y, which is b minus 2, b over 2. Okay, well, first for the first trajectory, well, we perform the dot product between the h vector and the differential of line. Since the differential of line and the, well, after performing the dot product, we get that it gives us just a y vector times x vector, which that gives us 0. So this integral will be equal to 0. And then for the from the 2 point 2 to the point 3, we perform the dot product, which will give us this h dy, like, for the second, right? And now that we have those two, we can easily get the other ones. For example, the 3 or to going to 4, it will also be equal to 0 because it will also give us a dot product between the y vector and the x vector. And as you can see, like, here is equal to 0, here is equal to 0, here is the h dy, here is the h dy. It's just changing in signs, right? And that's where I pointed out in the last one, that it's basically the same. It's the same as in the point 2 going to point 3, just changing in the sign because, well, when we perform the dot product here, it was here is going in the positive y-axis, and here will be going in the negative y-axis. So that's why in the final it's just changing the sign to negative, right? And then we perform the sum of integrals. Well, we perform the integrals, the sum of integrals, and here it gives us h minus b minus hb, which is minus 2hb, right? And now that we have that sum of integrals, we can perform the we can find the final value for the magnetic field. And when we for only to find the final value for the magnetic field, we just multiply this result times the permittivity, and then well, when we perform this multiplication, we get that the current is being divided by the B, and b is basically the length, and as we pointed out on the top, because of the 2D shape of the, well, yes, it's the value for the density. So we can replace that as the density on the numerator, of course, and get rid of the b on the bottom, the length, and then we get this final formula for the magnetic field that is negative and in the y-axis. Okay, now discussing briefly this in comparison to a current carrying wire, this magnetic this sheet produces a magnetic field that is uniform, not depending on distance from the sheet, and also that is discontinuous across the sheet with different field directions and all that. And this difference, well, is basically coming from the geometry of the sheet, because, well, an infinite sheet doesn't cancel out the same way like wires do, like we've seen in the past, in the second example, in the second exercise. And this leads to a constant field on either side. And also the discontinuity, it also like comes from the surface current, and yes, that's basically it. Okay, for the first situation, we have a particle and it has a uniform magnetic field going in the negative y-axis, and it has in the initial conditions, that it's basically when the time is 0, it has an initial velocity in the y vector that is just minus initial velocity, and it has also has a mass in the origin, and that's why the r vector in the initial condition is 0 in all axes, right? Well, in all vectors. So we have to use the Lorentz force law, and well, first of all we have to set up the, well, first of all I set up the vector for the velocity, and then we have to use the Newton's second law, and then, well, after we clear up the derivative of the velocity and include it here, and on the other side we have to perform the cross product between the velocity and the velocity vector and the magnetic field vector. After performing this cross product, we get that we have, well, this formula over there on the other side, and the derivatives of the velocity on the other side. And, well, we have to basically match them up, which is what I did here. Well, this is for the x-axis, the y-axis, and the z-axis, and we use basically yes, we use like this how to say, we use these these matches to set up a system of differential equations. And this system of differential equations, well, we have to solve it, of course, and we have to find the value for the velocity in x, right? So, well, after solving the differential, after solving, we have here like the derivative square, the qb over m square, and, well, finally, after solving this, we have to use the ordinary, well, after having this ordinary differential equation, we get from tables the solution, that is basically a cosine of qb over m over time, well, time, plus b sine qb over m time. And then when we have this for the x, we have to do the same for, well, we have to get also for z, using the matching here. We also clear setup, well, velocity and setup, and then we solve this dot product, and we know that the derivative of velocity in x is this here, and then we know that velocity in x is this here, so then when we derive the velocity in x, we get this, and when we cancel out with the product outside, we cancel out the m's and the qb's, well, some of them, not the ones that are in sines and cosines, and then we get this final result for the velocity in z. And then we have to do the same for velocity in y, but since we know that the derivative for velocity in y is 0, because we have it right there when we did the matchings. We just know that the derivative for this will be a constant. Well, I mean the how to say yes, the velocity in y will be just a constant, right? So now we go over here, and we have to do determine the initial conditions. That is basically when the time is 0. And well, basically when we cancel, for example, here, if we put here that time is 0, it will give us only 0, and so it's basically a cosine of 0 is 1, and b sine of 0 is 0, so b cancels out here, and we just get that a is equal to 0 here. And then well, basically yes, velocity in x is equal to 0, that is over there. Then velocity in y, you know, is a constant, so well, with the initial conditions that we had right here, we know that it's just minus velocity, initial velocity. So for By it's minus initial velocity, and for Bz it's going to be the same as Bx. That is basically the one we got here. We replace the t with 0. We get sine of 0 is 0, and cosine of 0 is 1, so we just get that b is equal to 0, so velocity in z is also 0. And then that will give us the expressions for velocity. Then we get the expressions for the position vector. We'll basically just have to integrate the velocity ones. Well, of course, for the position vector, position in x is the integration of 0, which is 0. For position in y is the integration of minus initial velocity and differential of time. So we just include, well, the position for y will be the initial velocity times time, and for the position in z, it will be also the integration of 0, which is going to be 0, and we get these final position expressions for the positions. That is position in x 0, position in y is minus initial velocity times time, and position in z is 0 too. And finally, for the acceleration, well, it's also very simple, because it's, well, basically we know that there's no acceleration, because, well, doing the derivative of 0 is going to be 0, derivative of the initial velocity is going to be 0, over time is going to be 0, and derivative of 0 is going to be 0. We have to derive the velocity ones, not the position, the velocity ones, to get the accelerations. But since, well, all of them are 0, we get that there's no acceleration. So finally, when we graph this, we will know that, well, it's going to be like this, because, well, the only vectors we could find were in the y-axis, and were for the position and the velocity, and that's it. Also, I forgot to mention, but the motion is not periodic, since there's not it's just a straight line. There's no circles or anything. Okay, for situation 5, well, we have a long straight wire which has a current that is flowing upward, and then we have a nearby rectangular current loop that is flowing, well, has a current that is flowing counterclockwise. Well, what we have to do is we have to find the magnetic field. Well, we have to find the magnetic field and the net force, well, by performing the sum of each force and, well, using the magnetic field of each segment in this rectangular loop, and see how it affects the wire. Well, basically, first, well, we have to, for the force at the point 1, well, at the segment 1, that is going from B to 0, well, B, from H to 0, we have to perform the integral. Well, we can get the constants out and perform the integral with knowing that the differential of line is in the z-axis. And when we perform this, also when we perform the cross product between the phi vector that was from the magnetic field here and the set vector that was from this, well, yes, this segment 1, we get minus rho vector. But when we perform the integral, we will also get a negative number for set, so the negatives cancel out, and we get the force in the segment 1 in the positive rho vector, and that's the final formula. Then for force number 2, we have to do the same, but in the integral limits, we have to consider the width of the rectangle. So basically we have to, well, as if we look at the segment 2, it goes from rho, only that rho, to rho plus width, that is the width of the rectangle. So, well, we perform the integral and also the cross product between the vectors, which will give us a positive z-axis because it's a positive rho vector crossing the positive phi vector. And well, also, well, when performing the integral, we will get the natural logarithm of the rho plus the width over rho in the positive z-axis and the constants outside, of course. Okay, and that's for force in the segment number 2. Then for the force in the segment number 3, well, it's basically the same as in segment number 1. It's just changing in the, well, it's going to change the sign because of the integral limits. Instead of going from b to 0, it's going from 0 to b, and that's why the sign changes in this case. And well, as we know, the cross, also the, how to say, the rho changes in this case. Instead of being just the distance from here to here, from the rho to the start of the rectangle, is rho plus the width. So that's why here in the denominator it changes in comparison to the first, that it was just rho. Here it's rho plus the width. So, well, we already performed this on top, and we get the same result just by it just changes in the rho and the sign because of, well, what I said about the integral limits, and it's in the positive rho vector. And for force in the segment 4 is basically the same, but with the comparing it with the force in the segment 2. We have, it's basically the same, just the integral limits changes, but we can leave it all the same, just changing the sign, and that's it. And the rho is the same too. Well, yes, it's the same vector for the rho. So yes, when performing the cross product, we get that it's this in the negative set axis, well, negative set vector. And well, when performing the final sum for the net force, we get that, well, we can cancel out these two forces because, well, this is the same as this but negative, so those two cancel out, and we just stay with the force in the segment number 1 and segment number 3 because, well, the rho's are different, and that's it. Also, it's in the positive rho vector, which means that in going into the graph, how to say, well, as it's in the positive rho direction, it's going to, it's a, how to say, a repulsion here, because, well, this wire has a force going to the negative rho direction, and this has a positive, well, has a positive rho in a positive rho direction. So that's why, well, yes, this means it's repulsing. If it was, for example, what we did in class, the example we did in class, it was attracted because the final result, final force, was in the negative rho direction. So yes, and also this means that in the, how to say, there would be no torque because of the same thing, that it's in the same direction of the how to say, the magnetic field is in the same direction as the total net force. So that would mean there would be no torque. And because of the angle would be 0. Yeah, that's it. Okay, for problem 6, we have to use the Lorentz force law to get, firstly, we have to get the value for the magnetic field at a constant velocity. For there to be a constant velocity, the net force must be 0, so we equal this Lorentz force law to 0. And then, we can clear, first we have to analyze the vectors and then make the cross product between the x vector and the z vector, which will give us a negative y vector, and the constants that were with these vectors were the velocity and the magnetic field. So when we clear up now that we have both vectors, both values in the y vector, we can then clear the value for the magnetic field, which will give us the electric field over the velocity. And now, in an alternate scenario where the magnetic field cannot be adjusted, we have to, first determine the cross product between the velocity and the magnetic field. We also have to determine the velocity with the magnitude and direction. And after we get we have to get then the values for the electric field and the magnetic field and the velocity field, the velocity vector. And after performing the cross product and equal, yes, and then we get here the electric field is in the y-axis, in the y vector. The magnetic field and velocity in y is in the x vector, and the negative of the velocity times the magnetic field, in velocity in x times the magnetic field is in the y vector, and all that is equal to 0, of course. And then we do the matchings of each vectors. So then we can clear the velocity and get the formula for, that it's, the final formula that will be velocity equal to the electric field over the magnetic field in the x vector. And then we have to, here I made the diagram that shows the electric field in the y-axis, in the y vector, the velocity in the x vector, and the magnetic field in the z vector. And for the magnetic field force, we also, we can, for example, here we can make the, we already know that the electric force is in the y vector, right, with this formula over here. And we have to prove that the magnetic force cancels out with this one. So basically, when we perform the cross product between the velocity and the magnetic field, we know that we will get a negative y vector, right? And this negative y vector, we get then the formula like this, like the negative of the velocity and the magnetic field. But then we also know that the magnetic field is equal to the electric field over the velocity. And velocity and velocity cancels out, and we just get the negative of the electric field. And so basically, when we replace that in the cross product here, we get that the force for the magnetic field vector is equal to the negative of the charge times the electric field in the y-axis, in the y vector, which is exactly the opposite of the electric field force. So this means that they both cancel out. One is in the negative y vector, the other one is in the positive y vector, and this means they will cancel out. So basically, if the electric is equal to the velocity times the magnetic field, they both will cancel out, and this is like our ideal values, right? So this functions as a velocity selector, because of this like cancellation, of course. And for example, if the this if this didn't have the ideal values, there would be like dominance. For example, if the particle speed was too slow, the electric force would have like a dominance over the magnetic force, and it will make a like a parabolic, something like that. And if it was too fast, if the velocity was too fast, the magnetic force would dominate and it would deflect the particle like in a like a transverse direction. And well, this selector velocity has a lot of applications in real life, and mostly in like for example, I imagine that it has applications in like the mass spectrometry, and the like providing like a velocity, like I think it has like a higher, it makes a higher mass resolution in those cases. Okay, for situation number 7, well, we have to calculate the total net force in this loop. And well, basically we know that the magnetic field is in the positive y vector, and we know that the formula for the force in each segment will be the current times the integral of the cross product between the differential of line, which changes in each segment, and the magnetic field, which is always that one. So basically, for the segment A to B, we have that the differential of line is in the negative y vector, and when we perform this cross product between the y vector and y vector, we will get that it's 0, as we can see here. And so this means that the whole force is going to be equal to 0. Then for segment B to C, we have the differential of line in the positive z axis, z vector, and when performing this integral, well, we know that the cross product between the z and the y vector is going to be equal to minus x vector. So when we also can get the magnetic field outside as a constant, and then we just perform the integral there, and we get this as the force for segment B to C. Then for segment C to D, we do the same, but here we have two different differential of lines. Well, we have this differential of line that has two elements in x. It has a negative differential of line in x vector and a positive one in the y vector. So when performing this cross product, this whole cross product, we'll get this final cross product between the differential of line and the magnetic field. And when replacing that, we can also do the same as we did before, and we just make the integral, and this will give us a negative value because, well, as we can see, it goes from c to 0. For example, here it's in the c point, and because of the differential of x, we have to see how it changes in x. Here it has a value in x, but when going from c to d, it goes from c to 0, because here in d is like alongside the wall, alongside the value of 0 in x, you know. So that's why it changes from positive to negative, because of the integral. And well, yes, integral limits. Then finally, for the segment from D to A is the same, that has one in Z that is positive and one in X that is also positive. When performing this cross product, we will get that right there, the magnetic field in the negative X vector and in the positive Z vector. When we get the magnetic field outside, because, well, we can get it out as a common product, common term. We perform the integrals, and we get this as the final force for the going from D to A. That is basically that one. And when performing the final net force, when we group all these terms together, we will get this final result. And well, since in the integration for the set, C and D are equal, then we can cancel it out, and then we will get that the final net force is equal to 0. Okay, see, this is the MATLAB code. Well, this line is just to define the variables that we will print out in here, and that will give us the formulas for the forces for each segment that we want to choose. This line is to choose the segment. Here I chose BC, but I will show with others. Here is to initialize the forces, the force, and here is just to, well, if we choose AB, this will be printed out in X, Y, and Z. If we choose BC, this will be printed out. If we choose CT, this will be printed out, and if we choose DA, this will be printed out. If we don't choose any of these, this will appear that we have to choose some of these. And well, if we run it, for example, with the segment BC, we can see here that it's there, the value of the force we got in the X vector. And for example, if we choose AB, it should give us 0 in all vectors, right? And there it is. And if we choose, I don't know, CD, it would give us in only the vectors that it has. There it is. And the A, it should give us in 2 vectors. There it is. And that's it.